Swayam Prabha. Digital India. Educated India.
So today, if we look at this course schedule, we wrapped up with topic 2.4 yesterday, and so I want to start with a little bit deeper dive into the what's under the hood with the unified effective width method today. I was able to chat with Professor Kalinaraman a little bit last night, and he told me that the new IS 801 is moving in the direction of using what's called the direct strength method. So you guys have probably studied that some. We're not going to talk about that so much. That's interesting to hear, and that makes perfect sense. The AISE 360, you won't see anything about direct strength method in there at this time or in 2027. I think it's going to be very interesting to see what the meaning of the AISI cold form steel specification falling under the umbrella of AISC is going to mean. I'm not sure whether there's going to be any sort of effort to unify the cold formed and hot rolled provisions in the U.S., or whether they'll look to maintain it as separate standards. Okay, so that'll be the first topic, and then from there, I think I want to, so the second topic you can say today is topic 2.6, and that's an essential takeaway I want you to have from the course. Is, okay, how can we design non-prismatic members? So that could be a stepped column and for a gantry crane, or various types of things. So then if you're looking at the schedule from there, the next topic says hands-on verification. This is tutorial session 3. I think it's going to be more effective to do that next week when we talk about the so-called general method, which I haven't really introduced yet. But I think that will, taking what we're going to talk about today and then working that, we're not going to change the problem very much. But I say, oh, I just did it by general method. Okay, and I think that'll help tie in with some of the discussion of general method next week. So I want to move that to next week, and we're gonna and then instead I'd like to skip to column bracing behavior and design today, and I'd like to do a few things there, and then conclude with a Consteel example that where we're going to evaluate stability bracing on an interesting problem. Okay, so that's the plan for the day. Let's see how it works. Okay, so the notes here are I think they're labeled. Let's see if I can read the screen here. Yeah, they're labeled 2_5. They're in the on the Google Drive, and so these are notes to get a feel for what's going on. So the first slide here is very much what I introduced to you yesterday, basically saying if we've got, I'm going to stand because then I can actually see the screen without the lights glaring off of it. So if we're considering the unified effective width approach, again, the mantra is we get an F critical of the column. Now, as I said yesterday, I should change my notes a little bit. If you look at the AISC specification, we're trying to move in the direction of using subscript CR for elastic buckling quantities. And so we've changed at least one thing there to FN. And so what I'm saying is F critical here is now FN. equals Pn over Ag. Okay, so given if you have a very long column, your stress at the column strength is relatively low, and so the unified effective width concept is that, oh, I have a very low stress, so I will likely have the plates will be more and more effective the lower and lower the stress level we're talking about. And again, I showed you the AISC effective width equation yesterday. So this is just one way one common way of writing Winter's equation. It's interesting, if you go to Eurocode, it's Winter's equation, but it's just written in a different algebraic form. The AISC uses this coefficient C1 in that equation, and C1 is equal to 0.22 if it's a unstiffened element, if it's like a flange of an I section. But then we want to try to get a little extra in terms of the capacity for webs or for HSS walls. And so we have coefficients of 0.2 or 0.18 for C1 for those. And so the way that a slender element cross-section members, their axial compressive strength is calculated in AISC 360 is we calculate Fn, or F critical here, based on the on gross section. We got a column stress at strength from the column curve formulas, and then based on the stress level, everything up to that point being based on gross cross-section properties, we go into the effective width formula. If we need to take some reduction in effective width, we calculate effective areas, and then the strength, nominal strength is Fn times the effective area. So that's what I illustrated to you yesterday. And okay, so actually this was the first slide, and this was simply saying that this method was originally proposed in the Cornell work by Pecos. That was a little bit subsequent to Dr. Kalyan-Raman's work with Pecos at Cornell. And the other thing here that I should highlight is that in the pages here, when I'm referring to figures in tables or equation numbers, these are entities that are out of the handbook for the Steel Bridge Design Handbook that is one of the documents in the Google Drive, Volume 4, and that chapter or volume is basically an attempt to explain from A to Z what is going on with the underlying basis of the strength design equations in the bridge standard. So very, very close to the building standard in AISC. Okay, so now, how do we make sense out of this approach where we use the gross section properties, we get an Fn, and then we take that to an effective width? If you think about it, if you're trying to work the problem by effective widths, just from logic, you would say, oh, so let me get an effective width based on my. You could say if that depends on the level of stress, okay, let me get an effective width based on the level of stress in the column, and then you might say, well, now I'll draw a sketch of the cross section with certain portions of the cross section treated as not being effective. Okay, and we're just showing the effective widths. And then we might say, okay, let's take the area, let's take the moment of inertia, any other cross-section properties we need for that effective section. Okay, and we would then take that to do our calculations for the column strength and so forth. Now the problem with that, hopefully if I can get you to see it, if you take that approach, you first need to go in and say, well, what's my level of stress this column is failing at if I want the strength? Okay, all right, so maybe I guess that. Then I go in and I get an effective width. Okay, get an effective width, I can work my cross-section properties. I think I can then go to the column strength curve. I can get then, so this is my estimate of level of the stress. Oh, that wasn't what I guessed when I started. So let me go back in again with that one, and I'll get another set of effective widths. I'll get another set of properties. I'll go back with those to the column curve again, and oh man, do I keep having to iterate this thing? So it's an iterative approach if we're going to take that type of logic to calculate a member's strength. And so that's what Dr. Pecos and his research team were initially doing at Cornell. But then they observed that, well, if we go through all that much trouble, in the end, the radius of gyration for flexural buckling, square root of I, effective moment of inertia over effective area, really isn't changing very much. So somebody then had the bright idea, well, let's just, if it's not really changing much, let's just use the gross cross-section to get our Fn, and then, oh, now we have a non-iterative way of calculating the strength. So that's kind of where that's coming from. And I can wave my hands even harder and say, okay, they also considered, well, what if we have torsional flexural buckling or other types of buckling modes? They concluded they could use the same trick there with the unified effective width method. They could get acceptable answers by using gross section to get Fn, getting effective widths, and then doing stress Fn times effective area, and that's the column strength. Okay, so that's the unified effective width approach that's used in the American standard. The Eurocode standard is different in its use of effective widths. There we focus on a cross-section resistance. So we go into the effective width formula with the yield strength. We get effective width, we get a cross-section strength based on that, and then based on gross cross-section properties, we calculate a chi reduction that gives us our member strength, right? So both using Winter's equation, but in a different way. All right, so I'm going to stand up again. Bear with me as I keep working around here so I can actually read the screen. So clearly the behavior that I've already emphasized a bit here is that when we have a longer column, the unified effective width approach, if the column is long enough, basically says we don't have to take any reduction for local buckling. So that's kind of what this is saying here. And the P0 term is a device to handle some various other things here in this Bridge Highway Design Handbook chapter. But P0 is essentially, for what we're talking about, is essentially a PY, FY times the gross area. And if we look at how the algebra works out on this, we can basically, after some algebra, we can write that, well, if we have a situation where we go in with F critical equal to little f, okay, and we calculate lambda sub r, our plate element non-cylinder limit times square root of Fy over F critical. And if the lambda is less than or equal to that, then okay, yeah, we may have had a slender plate element, but we're not going to have to take any reduction. So now, in terms of, that's kind of the way that works. I think many engineers will ask the question properly of, well, do we really have situations with hot rolled construction where we need to worry about all this? Well, and of course the answer is yes. We talked about beam type wide flange sections yesterday. And so those often will have slender webs in uniform compression. Also, the stems of a large number of WT sections, if we're looking at designing a strut that's a WT section. And one or both legs in a lot of angles will basically classify as slender under uniform axial compression. And then lastly, particularly in the bridge area, but also in the metal buildings area, we're often working with welded I sections. And once we're moving to using welded construction, either I sections or box sections, it's really not economical to have webs that aren't slender in a lot of cases. The economy is more into using a thin web. And so we need to address our unified effective width concepts in all those cases. Now with the post-buckling strength, and so in the terminology of the bridge standard, these are longitudinally unstiffened plate elements in compression. And I'm showing you two different cases here where the bridge standard would say the plate on the left here is a plate that's supported along two longitudinal edges. So this is what AISC refers to as a stiffened plate, but it doesn't have stiffeners on it. And then the plate on the right, that's a plate, according to AASHTO, that would have longitudinally supported edge, one longitudinally supported edge. The other one is free. And AISC calls this an unstiffened plate element. So as we talked about some yesterday, if we wanted to do some tests where we could set up rigging to provide those edge supports, simply supported edge supports, and if we wanted to compress these plates between the heads of a test machine, we would tend to get average stresses out within the mid-width of these of the plate there on the left that are smaller because we're losing stiffness due to the formation of these buckling waves in the plate. And then the plate on the right, that's our plate that has one of the edges is a free edge. Similar aspect, but in that case, basically we've got the highest stress at the supported edge, and then it tapers off to a lower stress at the free edge, where we have the largest amplitude of the buckling waves. So that's what we're working with. And we could ask the question of, well, how have engineers approximated this in the past? And so if we start with von Karman's work, von Karman basically suggested that if we have plates, he was looking at plates that are supported on two longitudinal edges. Let's replace the actual stress distribution by an effective width over 2 on each side, adjacent to each supported edge. And then the supported edge, we have basically a uniform stress F that's equal to the maximum stress for that average stress distribution that we were looking at earlier. So, so where we see the largest stress, capital F or little f here, we're basically going to use an effective width of that has that particular stress on it. And we can basically say that the effective width BE, we can determine that such that little f times BE times T is equal to the total load that's being supported by the plate. All right, so let's consider 2 strips as a rectangular plate, idealized in that way. Von Karman suggested he could estimate the maximum load capacity of such a plate by equating the elastic buckling stress formula, that you see here with equation 6.2.4-2, written with the B over T term as the effective width over T squared there, equal to Fy. So that would be the condition that gives the strength of the plate. So we divide that by the elastic stress formula where we're using B over T. And we can show then, okay, so this then means that the effective ratio of the effective width to the full width would be the square root of the elastic buckling stress over Fy at the ultimate strength, P equal to little f times BE times T. And of course, he would take little f equals to Fy here for this sort of a test. And so that's basically working with the idealization we see here in figure 51. All right, so Winter observed that that idealization of the strength was not sufficient to describe the strength he was seeing in physical tests, and the reason was because of geometric imperfections and residual stresses. So he proposed and verified experimentally what we've now affectionately referred to as Winter's equation. And so that's the equation you see in the middle of the screen here. And although there was actually a more optimistic equation that was originally proposed for plates transversely supported only on one longitudinal edge, I believe that was actually Dr. Kalani-Ryman's work. The AISI specifications basically decided to adopt just this one form, this equation that you see here, for all types of plates, both plates supported on one longitudinal edge or both longitudinal edges. And so that's Winter's equation with the 0.22. And then we've played games with that in the American standards since that time by manipulating the coefficient 0.22 and essentially either using 0.20 or 0.18 there. All right, so we defined this. We looked at some equations yesterday for the non-slender plate limit. And we had a bunch of other equations I showed you that were in the AISC standard. I would like to kind of show you what's going on in terms of the creation of those equations. And so if we look at this non-slender plate limit, lambda sub r, it basically is addressing the value of B over T, where if we are stockier than, if B over T is smaller than this lambda r value, then it's the plate's fully effective at Fy. And so then, of course, the strength would be Fy times B times T. So if we set BE equal to B on the left-hand side of equation 4b that we were just looking at here, so Winter's equation, just divide through by B, we can solve for the value of square root of FEL over Fy where that would be the case. So we're calling that, putting a special notation on that FEL, it's FEL-R here. And that's what the coefficient C2 that was showing up in the equations we're looking at is. And so from here, if we substitute into equation 4b for square root of FEL over Fy, C2, so again, equation 4b, that's Winter's equation here. So we're going to plug in C2 for each of the square root terms there. Then what we obtain is equation 6 here. If we basically simplify this equation, we say, oh, we've got a quadratic equation to solve for C2. And the solution that is the one we want for that quadratic is the one with the minus sign here in equation 7. So this is the equation that I flashed on the screen yesterday that's showing up in the AISC standard equations. We have the C1 coefficient, that was Winter's 0.22, and then we have values for different types of plates, 0.20 or 0.18 for C1, and then the C2 value is given by this quadratic solution. So now, if we solve equation 5 for FELR, so equation 5 here at the top, and we set, so then in that case we basically say, okay, well FLR becomes C2 squared times Fy, and we're working with, that's basically an elastic buckling stress when lambda is equal to lambda r. So we can say, well, let's equate that to the elastic buckling stress given that slenderness, lambda r. So that's what the third term is here in the second equation on the screen now. And from here, we can basically see if we move a lambda into the lambda squared into the denominator, then we've got the equation for FEL, the plate local buckling stress. And so we can say, well, the FEL at lambda r is equal to FEL times lambda over lambda r squared. Okay? But just basically some clever algebraic manipulation here. And focusing in on these four terms that we're saying that we can see are equal in equation 8, let's take the second expression and the fourth expression, and let's equate those and solve for FEL. So if we do that, we get this equation at the bottom of the screen here now, which I showed you as the equation to calculate the elastic buckling stress. So you might say, why don't we just use pi squared e kc over 12 over 1 minus nu squared over lambda squared? That's the equation we get from mechanics. Well, the desire was that Dr. Schaefer would basically develop this. He wanted to basically have the elastic buckling stress be calculated as a function of lambda to lambda r, or lambda r to lambda. So there we have it. We've got it in that form. So this is equation 7-5 in AISC. So now if we manipulate things a little bit further, we can, if we go back to this equation 8, and if we equate, let's see, the second and third expressions here in the equation, then we can solve, and if we solve that for lambda r, now if we want to try to understand, well, what sort of plate local buckling coefficient Kc are we working with? Okay, now we've got an equation for that includes Kc there in that lambda r equation, and so we're going to basically call that as a capital lambda r for 0.91 square root of Kc over C2, and that's our final coefficient that is showing up in the design tables for lambda r out of the AISC standard that we were looking at in working through things yesterday. Lot of algebra here. If we so given equation 7, so the equation for C2, and 10b, this capital lambda r equation here now, our specified value of C1 and the coefficient that we're employing in AISC and AASHTO for those expressions out of the design standard tables, what I'm calling here a capital lambda sub r. We can back calculate, well, what's the implied plate local buckling coefficient implicit in any of those equations from the standard. And so equation 10c allows us to do that. All right, so that kind of gives you a glimpse under the hood with what's happening with those equations. So a few other comments on how we're setting up here using the effective width method in the ISC standard. Winter also observed that although all the developments from von Karman and what I was showing you up here to this point, we're talking about the maximum stress, little f, being equal to Fy. Winter observed empirically that held reasonably well as an expression for what the effective width should be at lower stress levels. And although there are equations in the literature that would try to write that more precisely, that was the Winter's observation is, yeah, it's a reasonable estimate to use this equation with lower stresses also. So then we can write Winter's equation. We put in lowercase f, the actual stress condition at the edge, instead of Fy. And so this is applicable when lambda is greater than lambda r times square root of Fy over f. Then the last thing to show you is, I'm just going to kind of flash this very quickly. We've got these various cases where the different American standards use different coefficients C1 for various cases. And then I have a table that, if you're trying to glean what are these implied coefficients underneath the various expressions, we can understand based on what I was just showing you what we're getting from that. And we were looking at this plot and talked through it a fair amount yesterday. So this is the end result. If we're plotting we can say it's the nominal strength in terms of stress on gross area Fn over F, or effective width over the actual width. And then we have the one curve that's elastic buckling stress over F. We already talked about this yesterday. So we're plotting this versus the slenderness term, little f over square root of little f over FEL. And so I won't go back to describe all these again today. But that was in terms of the non-dimensional slenderness for the plate, square root of little f over FEL, the elastic buckling, local buckling stress. If we look at grade 50 steel, or 345 megapascals, if we convert this back to a B over T, so this is probably more useful often when we're looking at this as practicing engineers. So, okay, well, what sort of strengths am I getting for a grade 345 plate at different width to thickness? And this is for plates transversely supported only on one longitudinal edge, so basically a flange of an I section. Well, for different cases here, we get the blue curve, green curve, or black curve, and that is basically a function of the H over TW of the web, what implicit elastic plate buckling coefficient is being used within the equations. So 0.35 is if the black curve is if we had a very, very thin web. So we basically then are counting on a flange strength will be the black curve, whereas the top blue curve, that's that would correspond, Kc equals 0.76. That's a very stocky web. And so in that case, clearly you're going to get some benefit. So the plateau is going to be longer, but then still tapers off. The corresponding elastic buckling stresses are the dash curves. So you can see in all these cases, of course, for wider plates, we're getting significantly larger stress in terms of quantifying the strength than this theoretical stress at which it would elastically bifurcate out of plane. And similarly, if we have plates transversely supported on both longitudinal edges, i.e. if it's, say, a web of an I section, this is the situation I commented on earlier that, in my view, I don't see why we don't just use Winter's curve with the C1 of 0.22 and we just have the dashed blue line. But then as soon as I say that, it'll be pointed out to me that, well, there's some advantage to the other curves there, at least in the vicinity of where it starts to reduce from the plateau. And the plateau is measurably longer by playing around with those C1 coefficients. And so I think that's why the specification isn't moving in the direction of just using one here. The thinking of the specification committee is that, yeah, we should be using a different strength curve here for an HS section versus a say a box with or versus a case like a web within an I section. Okay, so that's kind of an attempt to give you a look under the hood at where were some of those equations that I flashed on the screen and we used yesterday coming from. Any questions there? Of course, you're probably using the direct strength method if you're working from the IS 801, so then all this is, I think we might get there eventually in the AISC standard.